So part C asks for what values of t is the particle moving down. So another way to phrase this question is for what values of t is dy dt of the particle's position equation negative. Because for the particle to be moving down, its y values have to be decreasing, so therefore dy dt is negative. So first thing I did was find dy dt in terms of t, which is the derivative in terms of t of its original t cubed minus 12t, and that equals 3t squared minus 12 by the power rule. And then I made a sign chart about dy dt's critical points, which are when 3t squared minus 12 equals 0 in this case, and that equals 0 when t is negative or positive 2. So those are my critical points in the sign chart. And when t is less than negative 2, dy dt is positive. When t is in between negative 2 and 2, dy dt is negative. And when t is greater than 2, dy dt is positive again. And so to answer this question, what we want is when dy dt is negative, because that's what we said before, and that's when t is greater than negative 2 and less than 2. So that's our answer. And then for part D, it said, where does the path of the particle have a local maximum or local minimum? So to answer this question, the path of the particle is another way of saying the graph of the parametric equation given for the particle in the xy plane. And so normal procedure that we have to find the local maxes and mins of any graph in the xy plane is to find the first derivative of the equation of the graph phrased y in terms of x, and then make a sign chart of that first derivative. So that's what we do here. And so to find dy dx, in the first two parts, we already found dy dt and dx dt. So we can just divide dy dt by dx dt to get dy dx, and that's 3t squared minus 12 over 2t. And then the critical points we use for a sign chart over here are when the equation equals 0, and that equation equals 0 when the numerator equals 0, and the numerator equals 0 when t equals positive and negative 2. And then the other critical point is when this equation, didn't show the work here though, is undefined, and that's when the denominator is 0, so 2t equals 0, and that denominator will equal 0 when t equals 0. So our critical points are t equals negative 2, 0, and 2. And so we make a sign chart of dy dx about those points, and this is what we come up with about those t values, sorry. And so there's just a catch to this, reading this sign chart though, is that normally if we're looking at a sign chart of y, dy dx, and these were all x values on the sign chart, we would say this here is a local minimum because it's going negative before it hits that point and then positive afterwards. But when we're doing our sign chart in terms of t values of a parametric equation, it's not necessarily what it appears to be, because these negative and positive dy dx values are in terms of a left to right direction of graphing, but we don't know for any given value of t, the parametric equation we're given, the particle could be moving in the right to left direction. So then this could be a local maximum instead of a local minimum. So we know just based on this sign chart that when t equals negative 2 and t equals 2, there's either a local max or a local min, but because we don't know the direction the particle is moving, we have to just put those t values into the original equation to test those points to see if they're maximums or minimums. And we don't have to test 0, we know, because 0 is not a maximum or minimum, because the graph has a vertical asymptote at t equals 0. So then I just plugged t equals 2 and t equals negative 2 into the original parametric equation to get 4, negative 16 and 4, 16. And so we know that both of these are either local maximums or local minimums. And this point has 16 is obviously greater than negative 16. So 4, negative 16 is the local minimum, and 4, 16 is the local maximum.